To speak about some recent developments that we have been doing for this electrostatic embedding QMMM formulation that we are doing in Marseille. So for those who doesn't know much about QMMM, electrostatic embedding means here that we are adding the QMMM interaction in the Hamiltonian, and that has a very long history in Marseille. So it started about 20 years ago with Nicolas Ferré, who implemented this ESPF QMMM electrostatic embedding method. Also, you can do a formulation with mechanical embedding. So he developed the equations and the code for energy and gradient and also micro iterations. And 2 years ago, I wanted to implement Hessian with my PhD student, Carno. So the initial plan was just to do that, but it turns out that we did many more things. So we implemented a couple perturbed equations for atoms, also the Hessian, but we also added grid derivative, charge conservation, a new link atom approach, vibrational spectroscopy, and an overall faster implementation of the equations. And that's what a bit what I'm going to talk about today. So just to motivate why would we care about using QMMM? So our main interest is in photoactive proteins. So here I show a lot of families of proteins that are photoactive, natural proteins that are photoactive. So yesterday we saw a talk by Massimo Livucci on rhodopsins, but I'm particularly interested in cryptochromes, which would be responsible of magnetic vision of certain migratory animals that can guide by perceiving the geomagnetic field. Also, I'm working on hemoglobins, which transport diatomic gases. And these are actually their natural function is not photo activated, but you can also dissociate the diatomic gas by absorption of light. So these proteins are not just single proteins, as I say, they are families of proteins. There are thousands of variations of these proteins in different organisms, but they all share a pattern of having a similar chromophore. So from retinols, we saw yesterday that rhodopsins, we saw yesterday that we have these retinols that do a photoisomerization. I'm going to talk today a lot on this chromophore, the main chromophore of flavoproteins, which is this flavin adenine dinucleotide. And this is the chromophore isoalloxazine ring, which can accept 2 electrons and 2 protons and get reduced. So it's involved usually in redox reactions. Well, the other ones, well, there are many other functions that are being done by all these types of chromophores. And if you want to treat that theoretically, of course, with classical force fields, it's going to be difficult because we need to treat the excited states of these chromophores. So QMMM is one of the well-adapted techniques to treat the excited states, and in addition, the electrostatic effect of the protein. So the QMMM approach will introduce us 3 main effects on the quantum fragment. The most obvious one is the electrostatic effect, in which the quantum density gets polarized and affected by the presence of point charges that are due to the surrounding protein. There is also a vibrational effect, what I call it, and with this I mean that the structure of the quantum fragment is going to be by steric effects hindered to a particular conformation due to the presence of the protein. And there is also a kind of long range effects, because usually these proteins do not exist in solution or in gas phase, but they form part of a very complex conglomerate of proteins, and they are usually also transmembrane proteins. And in fact, if you want to get a realistic geometry of the protein, you should consider all the surrounding properties, all the real surrounding of the protein. In any case, I'm going to speak about today about these first 2 parts. And just to be sure that we are understanding each other, the easiest way to understand, at least for me, that I'm not very expert on this field, the easiest way to understand QMMM is that we take the electron density and we map that into point charges. that we then insert in the electrostatic interaction, the classical term, the classical electrostatic interaction term. So here is the interaction energy. It's a sum over the QM atoms with their point charges derived with this electron density, interacting with the point charges. Okay, so we have an easy way to write that, a compact way to write that. So we can do the sum over the QM atoms of these point charges interacting with this external field due to the atoms. So if we want to insert this interaction energy inside the Hamiltonian, it's very easy also. We just derive this interaction energy with respect to the density matrix, and we get this easy expression because the only term that really depends on the density is the atomic charges. So the QMMM Hamiltonian is just a sum of these external fields with these atomic charge operators, and then we can insert that inside the Fock operator. So if we want to make this useful, we have to define how this atomic charge operator are. So we have to find a way to define our point charges, but that is one of the specialities of quantum chemistry. So there are many methods that exist in the literature. The most well-known is like the orbital-based methods, like the Mulliken population analysis, but there are also like Bader analysis based on the topology of the density. And finally, there are these grid-based methods called electrostatic potential fitting methods, which reproduce better the electrostatic field of the QM fragment. And that is actually what is used usually to parameterize classical force fields. So that's the one that we are choosing for defining our electrostatic embedding QMMM method. And just to explain you a bit how this grid-based method works is very simple. You just take the QM atoms and you define a grid of points around this QM atom. In each of these grid points, you calculate these electrostatic integrals, and then you fit these electrostatic integrals into point charges centered on each of the quantum atoms. So that is an overdetermined linear system of the equations that has a very simple formal solution. So we have a way to map these electrostatic integrals into point charges. This T here is this electrostatic kernel, is the 1 over R between the distance between the quantum atoms and the grid points. So with this atomic charge definition, we can just derive it with respect to the density matrix. So the only thing that depends on the density matrix is the electrostatic integrals, and then we can just add that in the Fock operator. So anybody that comes from DFT will already have a warning in his head by seeing that when you define a Hamiltonian on a grid, you can easily run into troubles, and QMMM is not different in this respect. And here I show you just the calculation of the atomic charges with this grid-based method along this torsion of N-methyl acetamide of two different grids. One which is not atom centered, so it doesn't respect really the symmetry of the molecule, and the other in an atom centered grid. So if you are not using an atom centered grid, so in this non-atom centered grid, you see a lot of a non-uniform evolution of your atomic charges, and also like it's not symmetric with respect to the zero. So the minus and plus degree, it doesn't lead to the same evolution of charges. Just by changing the way in which you construct your grid, you get very smooth and uniform symmetric curves. So that is usually preferred when you define atomic charges with such a method. So if you want to make a QMMM method really useful, you must not only calculate the energy but also the gradient. And if you are really a crazy person, you will also go to calculate the hessian to calculate, for example, vibrational spectroscopy. So the expression for the energy and the gradient in terms of this, so it's just deriving this expression. The gradient has two terms. One term which can be called like the classical term, in which the charge, the atomic charge is fixed, and we only vary the external field. And then we have another term which comes from the polarization of the density, which is the derivative of the atomic charge interacting with the fixed external field. So for the Hessian, we have a similar thing. We have a classical term, and in this case is the second derivative of the external field with fixed atomic charges. We have a first order polarization term, so the first derivative of the atomic charges, and then we have a second order polarization term. So if we just want to construct these gradients and Hessians, we need to derive the atomic charges. So this is the definition of this partial charge, is the nuclear charge minus the trace of the density with this atomic charge operator. And so if we want to derive that, this is a fixed term, so it gets canceled. So we just have two terms. One which is the coupled per term that comes from the derivative of the density, and then we have a second term that has a fixed density and is just the derivative of the atomic charge operator. So I'm going to speak first about the second part. And so that is also very easy to construct. So we take our expression of the atomic charge and we derive it. So we have three terms, one which is the derivative of this electrostatic kernel inverse. The other one is the derivative of the electrostatic kernel. And finally, we have the derivative of the integrals. But it turns out that this is a very inefficient way of implementing the derivative of the charge, especially due to the derivative of this inverse, which has a lot of contractions and is very cumbersome to implement. But we have a very easy way to work around that, which is before inverting the electrostatic kernel, we derive it first, and then we invert this T dagger T matrix on the left. In that way, we get an equivalent expression for the derivative, but in this time we have no derivative of our inverse. And it turns out that this just by this simple derivation, we have a 2.6 times faster algorithm, especially, and this is especially important when we do the second derivative of the atomic charges. So, well, just to construct this derivative, we need then the derivative of the electrostatic kernel and the derivative of the electrostatic integrals on the grid. And depending on which type of grids you use, you cannot easily include the derivative with respect to the grid. And if you don't do that, for example, if you don't use an atom-centered grid, and so you don't know what is the derivative of the grid with respect to the motions of the atoms, it turns out that you do not conserve the total charge. So the sum of the derivative should be zero. In that case, if we do not include the grid derivative, is not zero. And also we break the translation invariance of the energy gradient. So by using atom-centered grids, we can add these grid derivatives, and then all this charge conservation and translation invariance is respected. So to construct the charge derivative, we have this last part, which is the coupled per term. So we need to construct the derivative of the density matrix with respect to the atom motions. And here we run into a problem because we have two types of atoms. So we have QM atoms and we have MM atoms. That means that we will have two sets of coupled perturbed equations. These are the usual ones that are solved to get the Hessian. But these ones are the new ones that are appearing in the QMMM equations. And the problem of this is that the number of MM atoms is usually 10,000, 20,000. So that means that we should solve 20,000, so 60,000 times the coupled perturbed equations, which would make all this Hessian construction, Hessian building untractable. However, we found an easy workaround. So we solved an auxiliary coupled perturbed equation, which we are using only the charge operator. So the number of these equations is just the number of QM atoms. And then we just contract the solution of this coupled perturbed equation, auxiliary coupled perturbed equation for the MM with the derivative of the external field with respect to the MM atoms. And in that way, we reconstruct the rotation matrix that is used to build the derivative of the density matrix with respect to the MM atoms. So with this simple trick, we work around this bad scaling of the number of couple perturbed equations, and we only have to solve now of 4 times the number of QM atoms, which is usually a small number, the number of QM atoms. So having constructed this density derivative, the only thing is to construct now the total Hessian, and that we showed, in fact, for a very simple example of a small protein called chignolin, which is 138 atoms that we treat at the QM level. We soaked it in different water droplets, and we calculated the effort of calculating the Hessian, and we see that in fact we have a very beautiful almost linear scaling, so it's a scaling like 1.22. So that makes a very beautiful method. And so just to show you a bit of applications that we are currently doing. So as I told you, I will speak about these cryptochromes. These are flavoproteins in which we take the flavinadenine dinucleotide in the QM part and then the rest of the protein at the MM part. So just the first thing we did is to calculate the absorption spectrum. This protein absorbs in the blue. But if you just blindly take the lambda maximum as the Frank-Condon approximation, you predict that this protein absorbs in the UV. So it's not reproducing even the color of absorption. So what we did is to construct the Hessian and then construct the autocorrelation function for the harmonic oscillator and do the Fourier transform. And that allows us to compute the vibrational resolution of each of the electronic peaks. And so you can see in the black line is the experiment, and the red line is the vibrational resolve spectrum in proteins. So you have a beautiful comparison of all the peaks with experiments. This protein actually, when absorbs light, it gets reduced. So we get 1 electron, we form this radical anion, and then we can get a proton from the protein, and then we form this neutral radical, and then we can absorb another photon, and then we get reduced another time to form finally the fully reduced form. So we also computed for all these forms the absorption, vibrational results absorption spectrum. And just I show you the reduced neutral form, in which we reproduce very well from the black lines the first peak and the last peak, but we were missing a peak in between these two that was showing in the experiments. And in fact, when we considered the electron and proton donor from the protein, which is a tryptophan 409, then we managed to reproduce this peak in between. So that was like the first time that we give an interpretation, a realistic interpretation of the origin of that peak. Currently, we are also computing the infrared spectrum. Here I show the infrared spectrum of the oxidized form of the protein. And in order to analyze the complex structure of the infrared spectrum, what we do is to decompose the chromophore in fragments. So green is isoalloxazine, the chromophore, and then we have ribotyl in orange, and then we have the diphosphate in blue, and so on. And here we see that what is the contribution of each of these fragments in each of the peaks. And then we can univocally interpret each of the main infrared peaks in terms of their main contributions, in addition to the mixture between the different fragments. Usually what the experimentalists are using for photoactive proteins is what is called the difference infrared spectrum. So for example, in cryptochrome, when you start from this oxidized form and you put light, blue light, you get 1 electron and 1 proton, and you get this position here protonated. And when you do the difference infrared spectrum, you just get signals of this, of selective signals of this proton that you have introduced in the isoalloxazine ring, and you eliminate all the complexity of all the other peaks. And here we reproduce also that very well. So we have here a signature of the nitrogen, hydrogen out of plane motion, and here we have an NH bending mix with a CN stretching of position 10. So that also we reproduce very well. And finally, also we studied transition states in proteins. So for the reoxidation reaction, when you start from the fully reduced, it can react with molecular oxygen to form back the oxidized form. And we find, in fact, a very nice transition state, which corresponds to a double proton transfer, one from the isoalloxazine ring to the oxygen, and then this hydrogen gets transferred to the other oxygen to finally form hydrogenated, oxygenated water. So that's I'm coming to an end, and just to link back to the topic of this workshop. Usually in QMMM, you have this condition, in fact, that the number of MM atoms is much larger than the number of QM atoms. And actually, in our current implementation, we have a big problem because the QM program is sending the charges to the MM program. The MM program is calculating the hessian, it's writing it in communication files, and then it's sending it back to the QM program to do the normal mode analysis. So the main problem we have now is that this file, it has a very large size. So it has hundreds of gigabytes to terabytes, and that it takes hours and hours to write and read this file to send it to the QM program. In fact, it would have been much smarter if the MM program would have sent few information to the QM program to compute the QM part of the hessian, and then send back the information to the MM program, and the MM program would build the total hessian. And in that case, we only have a communication file that takes a few megabytes or several gigabytes, which is very easily read. So the only reason that we have this kind of implementation now is that we have these modules inside the QM program of normal mode analysis and construction of vibrational spectroscopy that is not present in the MM program. So perhaps a web-based modular interface that would do the normal mode analysis outside the QM program would be advantageous for us to adopt this strategy of calling the program from the MM and then doing this normal mode analysis outside. So this is a bit the perspective. So we are now implementing extra vibrational spectroscopies like Raman, vibrational circular dichroism, Raman optical activity, and so on. We are also collaborating, and I'm very excited about that, with Chel, Mike, and Senghun on an interface between mixed reference PIMFlip MM. And finally, also, we are now working on an extension of this QMMM method to periodic boundary conditions. And for that, we are searching for a very smart postdoc to contribute to this. So with that, I thank you for your attention.
Okay, thank you very much. So any question or comment? All right, then I have a question.
Yes.
So actually, how can you visualize the vibrational motion of MM part? Actually, you showed one slide of some
actually, I didn't show it here, but usually we do maps. Okay, so that in these maps, each atom is represented in a little box, and then we just put motions like positive as red and negative as blue, and so we can have a map of the motions projected on this structure.
Yeah, but you actually, in that slide, you specifically assigned the motion of some
this in fact I didn't include if you refer to this in here. I didn't include the protein motions. I just decomposed the QM fragment, the QM molecule in fragments. And what I do here is I calculate frequencies of the SAC blocks of the hessian, and then I do a decomposition of the total normal modes in terms of these local modes, local hessian modes.
I see. So you project it out.
Yeah, exactly. And then I can decompose the total motions in terms of these fragments.
I see. Thanks a lot. And any other question?
Yeah, sure. Okay. Miquel, very nice.
Yes.
Very nice talk. I was just wondering if you compare kind of your potential fitting method with just normal electrostatic embedding. So what's the difference? Is your method cheaper but less accurate? Is that fair to say?
Well, in fact, if we would do normal electrostatics, the trick of separating the coupled perturbed equations for the atoms wouldn't be possible. So if you do normal electrostatics, you have to solve the coupled perturbed equations for all the atoms of the system. So I would consider that for doing a hessian, that our method is much better. And then in ESP, I just showed like the lowest order in the electrostatic expansion, but you can map, in fact, the electron density not only to point charges, but also to dipoles, to quadrupoles, and so on. So that makes it much more compatible with, for example, polarizable embedding. And so all these efficiencies are still kept. And you just can expand your multipolar expansion to the order you want. So you can get a really accurate QMMM method in this way. It's systematic to include the QMMM interaction to several orders.
Okay, sounds nice. I'm sorry if my connection just broke, but so the QM calculation is of the isolated molecule, or the QM calculation knows about the point charges?
No. Well, you can formulate the two, but in principle, what we are doing is we are adding the interaction in the Fock operator.
Okay.
The only thing is that the atomic charges do not depend on the position of the atoms.
Okay.
So the point charges are derived only knowing the position of the QM atoms, and that's it. It doesn't know anything about the MM. But the density is calculated with the interaction included.
Okay, that's good. Cheers.
All right, then any other question? If not, then let's thank Miquel again and Emmanuel.